All right, everybody, it looks like it is just about time. So we'll start our second class today. And let me bring up a page that will kind of give an outline about what I hope to do this afternoon. So I've got multiple things for today. Let me share my screen real quick. It's over. All right. Nope, that's not the one I want. Okay, here we go. That's good. All right, so today we're going to, there was a couple of things that I didn't finish up on day one related to just a very brief general chemistry overview. So I didn't quite finish up molecular dipoles. We talked about bond dipoles and molecular dipoles. So we'll briefly finish that up. And then we're going to talk about acid-base chemistry with particular emphasis on this B, Lewis acid base, because that is kind of the basis of a lot of organic chemistry that we're going to see throughout the semester. And then we're going to jump into atomic carbon. We're going to talk about the different forms of atomic carbon. So is all carbon the same? Well, I guess technically that is true. Carbon is the same, but we have different allotropes, different forms of atomic carbon. The big one being coal. Most of you know all about coal, but diamond is another form of carbon, graphite, graphene, buckyballs, carbon black that they use predominantly in automobile tires, a lot of carbon black and pigments as well. Activated carbon for filtration is another one that is, let me go, live transcript is now on. So activated carbon is for filtration. And then, things like soot, you've all seen soot, whether it be in your fireplace, in your barbecue grill, maybe diesel exhaust, you've seen that black smoke that puffs out of the bus. That's soot. It's partially burned carbons. All right, and then we're going to talk societal about, especially, what role does coal play in our modern world? You may think coal is on the outs, but if you look at the use of coal, not just the United States, but I'm talking about worldwide, there's still a huge amount of coal being used, predominantly because of their heat content, and we'll talk about the heat. And then we're going to learn the very first organic reaction, which you already know about, called the combustion reaction. There's going to be a lot of different reaction types, but they can all fall within sort of three big broad categories. Combustion reaction is one of those that is under the broad umbrella of reactions that we call redox chemistry, oxidation, reduction, reduction and oxidation. So that's going to be a very important part of our understanding about organic chemistry. Huge amount of redox chemistry involved in organic chemistry, as well as other kinds of chemistries as well. But the other broad categories of reaction types that we'll see throughout the semester are substitutions and eliminations. Those are two other big, broad umbrella categories. And then there's a lot of subsets, just like there's a lot of subsets of redox reactions. We'll talk about the benefits of using coal and the challenges of using coal, and why perhaps we may want to get at least remove ourselves from the dependence of coal. Okay, so let us continue. And I'm going to stop the share. You know what? Let's go ahead and in the presence of time, because I want to show you the program that I talked about earlier. I want to introduce you to that ChemSketch program that it's in your syllabus, and it's in the Moodle page, because next week on Tuesday, we're going to begin the conversation on the hydrocarbons. So let me stop that share for a second, and let me just bring that up real quick. Where is it? Here we go, schedule. So here we are, Thursday the 13th. And here are the sections. You know, I hope you've had a chance to at least review that. I know a lot of that's redundant for you, but if you haven't had general chemistry in a while, I kind of really recommend that you go over this. And you don't have to memorize anything. I'm not going to test you on intricate details of general chemistry knowledge, but I think you're going to appreciate organic chemistry much more by having a fundamental understanding of those Gen Chem concepts. But here, where we're going to start on Tuesday, are the hydrocarbons. We'll begin talking about fuels, hydrocarbon fuels. But hydrocarbons are much more than just fuels. So this discussion is going to really rely on that program, that ACD ChemSketch program that we had discussed at the very first of the semester. All right, so that's sort of like a game plan of where we need to go. So I'll stop that share, and let's go ahead and get back to our iPad. Put that down. We don't need all that. Let me see if I can make this bigger. Full screen, that's all okay. Maybe that's about as big as I can make it. Hopefully you'll be able to see most of that. Let me get back to my ChemSketch. Oh, no, not that. ChemSketch. Where are you, ChemSketch? Let me stop the share and start that over again. Share screen. There we go. Okay. All right. So let's go ahead and talk about some things that we neglected in the first lecture. So let's continue our discussion of these topics here. Oh, Control plus is not going to do it for me either. Okay, that's all right. All right. So I know I had this bigger last time. Let me see. There's some way I can make this larger. Well, I'll work that out next time. Hopefully, most of you can see this. So last class, we talked about methane. Remember CH4, the very simplest of the hydrocarbon organic structures. And you see I've redrawn it here with all the dipoles. So we know that there are these bond dipoles. The electronegativity difference, chi, delta chi. The electronegativity of a hydrogen is 2.1. The electronegativity of carbon is 2.5. So the difference between those two is 0.4 for the CH bonds. So basically, I've got these wrong. Let me see. I did this wrong. Remember, our arrows always go towards the more electronegative atom. So let me go ahead and correct that for you right now. Hopefully I can do that without too much headache. So let me erase these arrows. Been doing organic chemistry for many, many years, and I still make mistakes, go too fast. So the arrows, remember, always go toward the more electronegative species. Here, here, and here. All right? So you see those 4 red vectors? If you sum all of those up, it nets to a 0. Because they all are in opposite directions from each other in terms of the whole structure. So if you added up these 4 vectors and their angles, you would find that the bond dipole is 0. And therefore, methane is nonpolar. By the way, methane, another word for methane, we oftentimes use in society, we call it natural gas. Natural gas. So this is maybe you have a gas stove at your house that runs off of natural gas, or maybe the heating system for your water tank. Methane, natural gas is a hugely important fuel to generate heat in society. Now, again, methane, just like carbon dioxide, is a greenhouse gas. So we want to minimize how much methane goes up into the air. Now, when you burn methane, you combust methane in oxygen, like you do in the furnace or in your water heater, you end up, or your gas stove, you end up making carbon dioxide and water. So, but methane as a greenhouse gas is actually even more potent than carbon dioxide in terms of just its raw power to affect our environment. All right, so we went from methane to water. Now notice that's tetrahedral carbon. Now notice the oxygen here is also tetrahedral, just like carbon is tetrahedral. All these angles being approximately 109. And again, this is a slightly compressed because these lone pairs, you see these 2 dots here, those are lone pair electrons. And they push a little bit harder than these. Now, fortunately here, I did do this correctly. So the hydrogen's going towards the oxygen. That delta chi is huge. Look at the difference here, 0.4 to 1.4. I know you don't have an appreciation for these electronegativity differences, but that kind of difference is massive. So these hydrogens here are extraordinarily delta positive. Remember the little delta sign? The delta means partial. If you had a full positive or a full negative, that's like in ionic compounds, cations and anions, if you remember that from your general chemistry. But these are not truly cationic or anionic. They're just polarized, but polarized in a huge way. So whereas methane is a gas at room temperature and pressure, water, obviously, at room temperature and pressure is a liquid, has a boiling point of 100 degrees Celsius to 12 Fahrenheit. Now, so these bond dipoles did not sum up to 0. They ended up with a new vector, this blue vector that you see here that's bisecting the oxygen, with this end of the water molecule being positive and the oxygen being negative. Now, think of polarity. The higher the polarity, the more the particles can stick together, either to themselves, just like in water. That's why water has such a high boiling point. For a molecule that has a relatively modest molecular weight, oxygen is 16, the hydrogens are both 1. So the molecular weight of water is only 18 grams per mole. But its boiling point for that size of a particle is huge. And that's due to this particular kind of hydrogen bonding that makes it very, very sticky with itself. Now, if you put water into, say, an alcohol. So now most of you are not old enough to drink, but if you look at that bottle of wine or vodka or scotch or whatever your parents' favorite drink is, you'll notice it's all one layer. The alcohol, therefore, must be very polar. The ethyl alcohol must be very polar. And truly it is. because it also has an OH bond. Now we'll draw ethyl alcohol later, not today, but we'll see that at a later time when we get to the alcohols. That's for a couple of lectures ahead. All right, now we also talked about carbon dioxide, CO2. It also had two massive dipole moments, just like there's two massive dipole moments here. Delta chi, by the way, of 1, that's a pretty big number too, also. So again, vectors having magnitude and direction, that vector cancels with this vector. So carbon dioxide is another nonpolar molecule, just like methane. Carbon dioxide is a gas at room temperature and pressure. So too is methane. Now, we do have liquefied natural gas. You've probably seen that on the news, right? You see these giant ships that are moving natural gas overseas. But what you don't understand or maybe realize when you first look at that picture is that those tanks are extraordinarily cold, massive refrigeration, and also they're under very, very, very high pressure. So you remember from general chemistry, the higher the pressure and the lower the temperature, you end up compressing the molecules, and you can liquefy things that are normally gases at ambient pressures and temperatures. All right, so we'll come back to this over and over throughout the semester. You know, this nature of bond dipoles and molecular dipoles, but let's have that nice foundation. Now let's continue to the second part of our conversation, acid-base chemistry. So I'll briefly talk about Bronsted acids and bases. That's protons, right? H plus, an H plus donor, that's an acid. Something that accepts H plus, that's a base. And then we'll get into Lewis acid-base chemistry, where we talk about electrons. So in that case, it's sort of flipped. The Lewis base, that's the electron donor, and the Lewis acid accepts electrons. We'll have some examples to show you right now. All right. So let's talk about this one first. Bronsted acid-base chemistry. H plus, donors and acceptors. Extraordinarily important. Important in biological chemistry, you know, shuttling protons back and forth. Exceedingly important. You know, if it wasn't for our blood being buffered, the sodium hydrogen carbonate CO2 buffer, our acid would fluctuate in pH. Our blood would fluctuate in terms of its pH extremely high and low, and that would destroy any enzymatic reactions in our system, and we'd quickly die. And there are conditions where people's blood pH is changed based upon some disease process. People who are severely diabetic can oftentimes get a condition called acidosis, where the pH, instead of being about 7.35, it drops more acidic, and that's a dangerous condition. There are other disease processes in which the blood chemistry is a little bit too alkaline, too basic. That's called alkalosis. And there are certain disease processes that lead to that. But now let's talk about the definition of Bronsted acids and bases. Two big types: strong acid base, weak acid base. We're going to talk a lot about weak acids and bases in this class, but let me just show you a reaction right here to demonstrate a Bronsted acid-base process. Here, I have two materials I'm going to react together. This one right here, this is what I call strong acid, is acetic acid. Don't worry about it. We're going to learn this molecule later on. But acetic acid is part of a broad class of organic molecules known as the carboxylic acids. And basically, this is very common for you. You've seen acetic acid maybe at the restaurant last night when you had a little oil and vinegar salad on your dressing, salad dressing. Vinegar is just basically 5% acetic acid dissolved in water. That's basically what vinegar is, okay? Now, I'm gonna react this with sodium hydroxide, NaOH, very strong base, okay? So sodium hydroxide is the acceptor, it's the base. You see what I'm doing here? Remember our arrows that we learned when we did free radicals in the first chemistry, where we made carbon-hydrogen bonds? I had a single fish hook because I was only moving one electron. Look at this arrow right here. Again, it's a curly. Curly arrows means movement of electrons. Now in this case, look at the top of the arrow. See, it has two barbs on the top of the arrow. That means I'm moving a pair of electrons. Now, many of you use dot, 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 dot to represent electron pairs that are lone pairs. In organic chemistry, we're big boys and girls now, we're going to use these lines. It makes it much more efficient. So where you see a line over an atom, that's a lone pair. So this has 1, 2, 3 lone pairs on this oxygen. Look at acetic acid over here. We have a carbon-oxygen double bond. Then we have these 2 lone pairs on this oxygen atom. This grouping here is called a carbonyl. We'll talk about that later when we get to functional groups. All right, so the base pulls the hydrogen off of acetic acid, making a new bond between that oxygen and that hydrogen. So you see this lone pair here? Now it's a new covalent bond. Where is it? There it is right there. Here's the covalent bond that used to be this pair of electrons. Now, we can only have one bond to hydrogen, so this has to break. So this pair of electrons, this bonding pair, becomes a lone pair on the acetic acid. And there it is right here. See this pair of electrons down here? So now there's a new charge on the acetic acid, so it's negatively charged, and therefore the counter ion now must move. So whereas the sodium positive charge used to be associated with this OH minus, now the sodium positive charge is associated with this negative species. So we went from a strong acid and a strong base to a weak base and a weak acid, okay? Now notice here, you see this line here? You can't even see this, what's down here. This is a line going the opposite direction. This is done by design because the equilibrium is way, way, way on the side of the products. Remember equilibrium, K, KEQ, KSP, K anything, capital K anything, is just the products divided by reactant concentrations. So these brackets mean concentration, okay? So K in this case is way, 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 way bigger than 1. It's probably on the order of like 100,000 or maybe even more than that. I'd have to look at the individual equilibria for these. But essentially, we have all products, almost no reactants. That's why I drew this teeny, teeny, tiny little back arrow. But theoretically, all reactions are reversible. But in this case, you can almost just assume this is a complete transfer of the proton from acetic acid to the hydroxide to make acetate. That's what we call the anion of acetic acid, acetate. Again, I won't ever ask you that, but sometimes it's nice to be familiar with the language. And then water being the other product, okay? All right, now, in a weak acid, weak base, then we have a weaker base and a weaker acid, where the equilibrium may actually reside on the starting materials side. So here's the starting materials, and these are the products. Now let's go to our big one now, Lewis acid-base chemistry. Now, this molecule here is called furan. I know this looks very strange to you. It looks like a pentagon where one of the apexes is an oxygen atom. In organic chemistry, we're going to learn how to write an abbreviated form known as the line notation. So I'm going to throw this out there right now, but don't worry about getting this because I'm going to do a lot more of this on Tuesday. So basically, what these line notations show you is that everywhere you see this intersection of two lines, that's a carbon atom right there. That's a carbon atom. That's a carbon atom, and that's a carbon atom. Now, in organic chemistry, we don't draw the hydrogens. They're implicitly, we just know that by knowing that carbon needs 4 bonds. So if that carbon atom right there has only 1 bond, a single bond to the oxygen, a single bond to the carbon, therefore, what I implicitly know is that carbon has 2 hydrogens on it right there. This carbon has 2 hydrogens because it only has 2 bonds. That carbon has 2 hydrogens and that carbon has 2 hydrogens, okay? So that's just a little sidebar on line notation, but that's not what this slide is about. This slide is about electrons. Electrons, which are these lone pairs on the oxygen, adding to this boron trifluoride, BF3. BF3 is a very powerful Lewis acid. Remember what I did? Now here's where you do have to know some definitions. And don't worry, before the exam, I will tell you, you'll have a chart. You got to know this word. What does this word mean? So a Lewis acid is an electron pair acceptor. So the pair of electrons is coming from here to the boron. So this is going to make a new bond between this pair of electrons and the boron. So that pair of electrons now is a new covalent bond. And that's going to generate charges here. The boron's going to become negatively charged, and the oxygen will become positively charged. Don't worry about the charges yet. We'll show you how to do all this electron bookkeeping later. But basically, I have a new kind of covalent bond. See the bond right there? Rather than the definition that we learned in the first class, where 1 electron from one atom and 1 electron from the other atom combine to make a covalent bond. Here we have none on the boron, 2 from the oxygen, making a bond. That's called a coordinate covalent bond. We see it a lot with metal chemistries, and we'll see some more of this. But that's the basic understanding of Lewis acid-based chemistry as it applies to organic chemistry. A pair of electrons donating, that's a Lewis base, and a pair of an electron pair acceptor, which is the boron. Later on, we'll show you where did those electrons go. They went to a vacant p orbital. This boron, I know I don't show it here, but there's a vacant p orbital on that boron, and that's where those electrons are going into. All right, so that's basically our review of organic chemistry. So let's go back. So we're finished up with all of this stuff here. We're done with that. So remember, I do assume that you know some basic general chemistry from your 101 class. And again, probably pretty rusty for a few of you. See quite a few seniors in this class. So you may want to kind of bone up on some of that Gen Chem. All right, now let's go to B, the chemistry of atomic carbon. Now, it's kind of strange. The basic atom of all of organic chemistry is actually not considered organic. Okay, it's not organic. There are many other compounds of carbon that we don't consider to be organic. Do you remember the carbon dioxide? Now, methane is organic. It's called a hydrocarbon. Water is not organic. There's no even carbon in there. But here, look at carbon dioxide. It has a carbon in it. But carbon dioxide is not considered an organic molecule, okay? So not everything that contains carbon is organic. There are some exceptions. But most of the time, we're going to use the loose definition. What is organic chemistry? The chemistry of carbon. All right, so we're going to talk about right now the basic of all organic chemistry, carbon. And now the first one, by the way, before I leave that, remember I talked about all these different allotropes? Kind of slow. There we go. So I'm not going to really talk about diamond or graphite or buckyballs or carbon black or activated carbon. These are all also forms of carbon, and they all have their particular purpose. So diamonds, obviously, you know, if you ask somebody to get engaged, sometimes you'll give them a diamond ring. Graphite, you know, is probably the pencil that you're drawing with right now. Graphite has a different form of carbon, very different than diamond. I think if you gave your girlfriend or boyfriend a graphite ring, they probably would not be pleased. Diamonds are rare, and that's why they're expensive, and they have a much different structure, and they're very, very hard. And that's why sometimes we use diamond to cut things. So you'll see diamond tipped saw blades, very, very hard, so they won't fall apart when you're cutting something that's really hard. Buckyballs and carbon black, you know, I already told you about carbon black being in automobile tires and pigments. Activated carbon, that's a very porous form of carbon. It is important, but it has kind of a niche role in society, very important industrially, you know, when it comes to you know, absorbing gases and cleaning up things. So we use it as a filtration aid. Soot, obviously, soot has a checkered history. Soot can be very carcinogenic, and we'll see that too. All right, so let's continue on. Oh, nope, not quite yet. All right, so let's talk about coal. Be able to somehow make this bigger. Well, this is something I have to work out. You won't be able to, let me see if I remove the frame, if that helps. Helps a little bit. Yeah, a little bit, okay. So coal, what is coal? Coal is organic material. And you can't see this chart, but if you, let me see if I can make this bigger. Oh, there we go. I can do. Okay, good, good. So I just got to use 2 fingers. All right. Sorry for my technical, not so technical at all, but my skills are going to improve as this course goes along. So how does coal form? So we have organic matter. Here's peat. By the way, there's a lot of societies that use peat to heat things. If you go to Scotland and Ireland, they have a lot of peat bogs over there, and they will cut these blocks of peat to heat and cook their food and heat their homes. And in Scotland, a lot of times they will use peat to take the grain and germinate the grain. And that's very, certain scotches are very peaty. They have a smoky flavor to them. And again, your parents would know about this, but you're not old enough to know about scotch. So just ask your folks about peaty scotch. Now, this gets compressed. Once this buries, look, pressure, 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 heat, and time. So this eventually will become lignite. Some people call this brown coal, brown coal. Then more and more pressure and deeper in the environment, then you get this bituminous coal and subbituminous coal. And then eventually that compresses, and you get bituminous coal. And eventually that compresses, and you get anthracite coal. And this is the expense also. So in terms of price, anthracite coal is the most desirable. It has a high heat content, high carbon content. And let me pull this up a little bit. A little bit too much, sorry. So here's anthracite coal, and you see it has a high heat value, the BTUs per pound. And then these have a little bit higher heat value, but we're going to talk about why some bituminous coal is a little bit less desirable. And that's because it has other impurities in there, like sulfur and heavy metals, or at least a higher load of heavy metals that anthracite has a lower concentration of. So if you go down, here's kind of a description. Anthracite coal is very shiny, hard black coal, high carbon, high energy density. So very good. Now, smokeless fuel, this is not true. If you heat anthracite coal, you will get smoke. I have a bag of anthracite coal out by my fireplace that I use to start the wood, and it'll put out some smoke. Bituminous coal is, again, softer, shinier, a little bit higher moisture content. So they call these coking coals. We'll talk about steel later, but steel making involves a lot of heat and energy, high carbon steels, the volatile matter. So for heating, sorry, and metals, very important. Then obviously, as you go down, brown coal is the lowest. It has a low energy density. We use it for power plants because it's cheap. So big electric power plants use a lot of lignite coal. It's more available. It's closer to the surface of the earth, so you can just basically knock the top of the mountain off. There's a lot of lignite coal in there. To get to the anthracite coal, you got to dig. You got to mine it in tunnels. So this is not so good for the miners because they got to go deep under the earth. This is not so good for the land because now you're just destroying the tops of the mountains in West Virginia and Pennsylvania and Ohio. So that's that. All right. So coal.
Dr. Brown, I have a question.
Sure.
For the coals and stuff, do we need to know like the definitions? Like, is that what's going to be on the test, or like what part of this would like
No.
know?
Just if I give you this table, what I would ask you is what's the differences between anthracite and lignite coal? You'll have the table, you'll have this data. Now I won't give you this stuff down here, but at least you should know just in broad terms that there are different kinds of coal, from very sought after expensive coals, anthracite, to the very widely available brown coal that the power plant uses. So that's, and again, before the exams, I'm actually going to guide you into what I need you to know. So you don't have to do a lot of memorizing right now. Basically, I'd like you to get some understanding and appreciation. If you've never heard of coal before, some of you maybe, I know you know coal, but you don't know it to this level of detail. But here again, we're going to talk about in a moment the possibility of some of you may want to do your project around coal. And we'll talk about that. I'm getting ahead of myself here. All right. So again, you don't have to worry about knowing all these definitions or the heat values. So let's talk about the reaction before we get anywhere else. So combustion reactions, especially what we call complete. Complete. What does complete mean in the presence of combustion? So a complete combustion means all of this carbon reacted with the oxygen from the air. Typically this is air, though it doesn't necessarily have to be. You could, some plants, some metallurgical plants that need very high heat, they'll inject, O2 as a liquid, and that creates a huge amount of heat. But complete combustion means it all goes to CO2. So obviously this is a balanced equation, right? One carbon on the left, one carbon on the right. Oxygen, O2. Two oxygens here, two oxygens over here. Now, obviously, there's been some bond rearrangements going on here. We used to have a double bond oxygen here. Now we have two carbon-oxygen double bonds in the product, as we saw in our Lewis structures. But here's the big thing. So the CO2, bad, right? We all know that that's a global emission gas. So we'd love to be able to trap this. We want the heat, but we don't want the CO2. And companies have spent an enormous amount of money on technologies that can trap CO2. Unfortunately, with only very modest success. So we still have a long way to go. So the heat, what do we do with this heat? Well, we do a lot of things. The big thing we do with this heat, especially with the brown coal and the electric power plants, this heat generates electricity. Basically, an electrical power plant is nothing more than a big turbine with two different kinds of magnets, a rotor and a stator. And that generates electricity. So the steam turns a turbine, and the turbine spins. The magnets go around and around, and then there's a permanent magnet on the outside. And you remember from your physics class, a changing magnetic current generates at right angles to the magnetic field and electrical field, right? That's electromagnetic movement. So you're generating electricity in the power plant by using turbines, steam turbines. Now, if this was pure carbon, then coal would generate pure, you generate only CO2 if it's a complete combustion. But the problem is this reaction is never complete. So we get other products. And the products of this is coal ash. Coal ash is fraught with issues because this carbon, even this really fancy anthracite carbon here, this really expensive carbon, it has heavy metals in it, arsenic, chromium, lead. So if you live near a power plant, and this has been proven, there's a much higher incidence of cancers near coal burning power plants. So coal ash is also a problem because what do you do with it? So after you burn all this carbon, you put it in a giant lined pit. Now, most of the time, that's okay. So as long as there's no issues, that's all right. Now, the other thing that you'll notice about a lot of power plants, they're located typically along rivers and lakes because they need the water. They absolutely have to have that water to run efficiently. So if that river should overflow and that water goes up into the ash pond, it can actually overflow that ash pond and cause all this chromium and arsenic and lead and other heavy metals to get into the groundwater. And that groundwater can go down and go into the river, into the people's wells that live nearby the power plant. So all coal plants have to have monitoring stations around them. All electrical plants that burn coal, they monitor their ash pits. So this is a huge, huge downside for the burning of coal, okay? So we got the carbon dioxide problem, we got the ash problem, so it's less desirable. All right, now I want to tell you a quick story about coal liquefaction. There is a technology where you can take carbon with hydrogen gas, under heat and pressure, and you can convert elemental carbon into liquid fuels. This is called coal liquefaction. There's direct liquefaction and there's indirect, and we're not going to get into the technology. If you're a chemical engineer or an environmental engineer, okay, you can go ahead and look at that. But that's not important for what we learn. Back in World War II, Hitler needed fuel. They did not have a lot of petroleum. They couldn't pump. We'll talk about petroleum next class, by the way. That's a hydrocarbon fuel. Petroleum they needed, which they couldn't get. The Allies blockaded Germany, so they could not get the fuel. But the German chemistry industry was very, very adept at taking carbon, which they had huge abundance of coal in Germany, and they turned it into jet fuel for the Luftwaffe. They turned it into diesel fuel for the tanks and the jeeps and the trucks. So had it not been for coal liquefaction, the war would have ended much earlier because the Germans would have run out of fuel. The Allies knew this, and so one of the biggest bombing missions they had was to bomb all of the coal liquefaction plants. That was a huge target for the British and Americans and Russian forces to get at those liquefaction plants to destroy all of the basically that was the engine of their war machine. So again, look at this, coal is part of this whole industry. I'm just gonna quick look at these chats to make sure I'm not missing something here real quick. I'll try to answer some of these chats after we talk today. Sometimes, when I get going, it's hard. I will leave about 10 minutes after, before the actual end of the lecture for questions and answers. So if I didn't answer it, I'll try to get to it. Okay, let me get out of my chats here real quick. All right, so let us continue. So coal, vitally important. Now let me stop the share real quick. In your Moodle page, share screen again and get a different one. Let's see here. Where is Moodle? Do I not have it up? Looks like I don't have it up. Let me pull up Moodle real quick. That's the syllabus. That's that. Yeah, I don't have that up yet. I'm going to pull up Moodle real quick. wolfer.ncsu.edu. That's our big one. Okay. You probably have other Moodle pages, I'm sure. I just have one. Okay, it's coming up. Patience, patience. Okay, here we go. Now let me get back to my meeting here real quick. Share my screen. Get to Moodle. All right. So here's my Moodle page. So many disclaimers. Okay. Now, if you come down here to the organic chemistry of fuels, the first part of this, so if you click on this, the first part is going to give you some of these videos. Now, you don't have to watch any of them if you don't want to. But if this topic is interesting to you, here are a few places that you can go to look at some podcasts and other things related to carbon. This particular one down here has to do with soot, by the way, not really energy. This is about the chimney sweeps in England that used to get cancer from soot. Pretty interesting, actually. That's coal dust, obviously. So when you burn coal in the chimney, you get all this dust up in the chimney. And they used to send these little boys up there to clean out the chimneys, and they would get cancer. So that's kind of interesting. So keep that in mind. Get on your Moodle page. I'll populate these as time goes on. Obviously, a lot has not been populated. So if we go to part 2. Well, actually, the organic molecules beyond Earth, I put a couple little links there. But you'll see a lot of these have nothing in them. As the semester goes on, these will get populated. But given they gave me this course with 3 weeks before the semester started, I haven't had a chance to develop this very well. But those will come. All right, so let me stop that share. Share something else with you. All right, continue. Good. Now let's go to down here, the benefits and challenges of coal. I want to talk about why we used coal. You know, obviously, traditionally, back in the Industrial Revolution, coal was vitally important to us. But coal, as I said, has significant issues with mining operations. Whether you are going what they call strip mining at the surface or going underground to get that expensive coal, you're still hurting the environment. So that's one challenge. CO2, we all know about global climate change. If somebody tells you it's not real, that it's a hoax, send them my way and we'll have a nice discussion. Or maybe even if you believe that it's a hoax, we should have a talk. And I will listen to you, open mind, and hopefully you'll listen to me with an open mind. I've had discussions with a lot of friends of mine from back in graduate school and other places, and they have certain opinions about global climate change. But take it from me, it is a real thing. All right, coal ash, we've talked about that. Heavy metals, where do you put it? Do you landfill it? You know, that's the big problem with coal ash. When we get to next week, we'll start talking about natural gas, methane as a fuel instead of carbon, coal. And obviously, when you burn methane, you don't have coal, you don't have any ash. So there's a big advantage right there. The economics, this last one of coal. Coal's going away. I know President Trump said, you know, coal's coming back and, you know, hoorah for the miners. And I have a lot of friends from West Virginia, so I can empathize. And so if you have your whole history and family history involved in mining coal, you have to be receptive to the people's wishes there. And if they hope that coal will be around, then we just have to believe them. But the economics nowadays say that coal is not going to be around much longer. Plants are closing every year. There are far less coal plants now than there were just 10 years ago. The mining industry is going way down because the money is not there. It's just too expensive to burn coal these days compared to burning methane for the heat. And it's actually more expensive than environmentally friendly sources of energy like wind and solar. So we'll have that discussion too when we get to those topics. So economically, carbon is going away. All right. So we have finished the formal part of today's lecture in terms of the chemistry items that I wanted to talk about. Now, one thing I do want to talk about now is that program, the ChemSketch program, because we're going to start using it next week. And if you're a Mac user, hopefully you've gotten on to the site that will allow you to download ChemDraw. ChemDraw is a very powerful program, and the university provides it to you, by the way. You should not have to pay for ChemDraw. The university has a license for ChemDraw, and that's very friendly for Mac people. By the way, PC people can use ChemDraw too. That's certainly fine. All right, so let me stop my share here, and let me open up the ChemSketch program. So if you've downloaded it, and hopefully you got the freeware version, you didn't pay for it, this is what you come up with. Here's the page called ChemDraw. And this is the blank document page. Now, in addition to ChemSketch, there's a sister module that's embedded. Oh, I don't know if I'm sharing my screen right now. Here, hold on a second. Let me go back here. Make sure I'm sharing my screen. Screen share. Chem sketch. Enter. Okay, sorry about that. So here is the blank tapestry for Chem sketch. I'm going to minimize this so I don't see everybody. Now, notice on the left-hand side, there are all these atoms, these different atom types, carbon, hydrogen, nitrogen, oxygen. So here's some non-metals up here. Here's some metals, sodium. Silicon's a non-metal, phosphorus is non-metal, sulfur is obviously non-metal, chlorine's not a metal, potassium is a metal.
We can't see it.
You can't see that? Stop share. Wonder why you can't see that. Let me try that one more time. I don't know why Chem sketch is not coming up here. Share screen. Chem sketch. Where is it? Let me see. Why is that not coming up? It's odd. Okay, let me go here.
It said you were sharing your screen. We just weren't able to see it.
Can you still don't see it right now?
Oh, I see it now.
We see it now.
Yeah,
Oh,
we can
thank
see
goodness.
it.
That would have been a disaster. Okay, good, good, good. I'm glad you can see this now. So this is the Chem sketch, the blank piece of paper that you will draw your molecules. Now again, Chem sketch is 2 modules. There's this flat piece of paper, and then there's also the 3D module that underlies this, and I'll show you that right now. So let us go ahead and draw a simple molecule. Let us draw methane. So you see over here, that's carbon. So I'm gonna click on carbon. I'm gonna come over here, I'm just gonna tap it. There's methane, CH4, okay? That is just the formula for methane, okay? It doesn't show any of the bonds, it doesn't show any of the angles. It's just basically the molecular formula for methane. Now, what if I wanted to draw this out and see things? So if you look up here, there are all of these tools up here. I'm gonna pull this over. Sorry about that. I'm gonna pull this down a little bit because I'm having trouble seeing a few things here. Is everybody still seeing my drawing paper here? Okay, good. Okay, edit, undo draw. You can always undo. Now, let's see here, pages. I'm gonna go ahead and save changes. No, I'm not gonna save that change. Okay, I'm gonna pull that back up again. Share screen. Let's get to ChemDraw. Share screen. Oh, share screen. Share screen is not coming up. All right, let's keep going. Technical issues, always technical issues. So let me go ahead and bring up Chem sketch again. Sorry about this. We'll get there. I guess you're just seeing the whole class page right now. So I'm going to go ahead and bring up Chem sketch one more time. All right, now, okay. Share screen. Can everybody see it? No?
We can see it.
Okay, good, good. Let me go ahead and put carbon again, right there in the middle. Now, do you see way up here, there's all these different tools and templates and add-ins. So I'm going to look at some of these and we'll just go through a few of them. And what I want you to do between now and Tuesday is get in. You can't hurt anything. Just practice. So here's some things like structure properties, what kind of atom sizes there are, so you can look at those. Now, what I want to do here is I want to go down here and you see 1, 2, 3, 4, fourth one down. See this thing that says 3D structure optimization? So I'm going to apply that to the methane and watch what happens to the methane. There it is. See that? So now what just happened was it turned that around. Now I can rotate this too, by the way. So I can just hold it and spin it around. Can everybody see? It's kind of hard, but doesn't it look like it's tetrahedral there? No, not so much. Okay, well, that's okay. So again, I can change also the view, by the way. So I'm going to look up here and I'm going to view this in a different way.
On my desktop, the only thing that
Let's see here. I can number the atoms if I want to. So I can remove the explicit hydrogens, go back, unremove hydrogens. I can cut and paste stuff. I can structure, I can draw different things, other like arrows and reaction arrows and other figures. So that's this drawing versus structure module. I can, let's see here, tools, templates. I want to show this in a different way. So options, templates. Clean that structure up again. Pages, edit, file. You can save things too, by the way, if you want to save your structures after you're done. But what I want to do now is I want to show this with some different kinds of properties now. So I'm going to go ahead and clean that up. Now, if you go way up here, right next to where this PubChem thing is, this thing that says PubChem, if you go to just to the left of that, 3D viewer, that's going to take my methane molecule and throw it out into the 3D viewer program. So let me go ahead and do that. I'm going to take methane and put it into the 3D viewer. Now there's a lot of other stuff here. Don't worry about a lot of, you can browse around again, you're not going to hurt anything. But I'm going to go ahead and put it into the 3D viewer. Takes a minute to come up. Okay, there it is. Now, what I want you to notice, let me expand this out a little bit more. So right now, this is called a ball and stick. This is called a ball and stick. So you see this view here? I can show this as a lot of different ways. So what does wireframe mean? Well, I'll just click on it. It's going to change your structure into wireframe. There's the carbon in the middle. Here's all the hydrogens. Now I'm going to view it as sticks, just sticks. There it is, sticks. View it as ball and sticks. But you notice, look at here. If I spin this around, by the way, you can spin it around with these auto rotates. But see right now, everything right now is flat. Remember I said that that's not right? It's showing it as flat and planar, but it's not. So if I want to show it in 3D, I have to come over here and do 3D optimization. Now it's
Hey,
3D.
once you the 3D model, it froze for everyone.
Oh, it did? Oh, okay. Can you see my molecule? Methane? No? Yeah.
So we can see it in the chem sketch, but we cannot see it in the 3D viewer window.
Oh, you can't? Okay, let me stop the share and let me see if I can share the screen again. Let me see if how's that look? Better? No.
You can
Yes.
see it now.
Yes, now
can
we
see it
can
now?
see it in the. Mhm.
Perfect. That
Oh,
looks great.
perfect. Good, good, good. So here's methane again in the 3D viewer. So again, you didn't see this earlier, but let me go up here I'll show you wireframe. That's what it looks like, wireframe. And by the way, how I got this is I had to come up here to this 3D optimization. That's what this is, 3D optimize. So now everything is in the molecule. Now view it, ball and sticks. I can change it to ball and sticks. I can change it to dot structure. This is the van der Waals, by the way, the van der Waals radii. So this has sort of the electronic nature around the atom. So obviously these are the carbons and these are the hydrogens. I can show this, I can view it as disks. There it is in disks. I can view it as space fill. There's the space fill model with shading, very nice. But you know, for me, I know all that's really fancy and nice, but for us, how about we look at balls and sticks? Because I think this gives most of the information we need. It shows us the three-dimensionality of it. Now, remember it was methane, right? CH4. Where's the other hydrogen? It's behind the carbon, isn't it? If you're worried about that, you see up here where it says auto rotate, change style. That will change style. So it'll go from sticks to balls to, don't choose this one. Choose the one that's right next to it. Just the one that says auto rotate. Now, your computer is going to be much better than mine. I have a very old laptop with a very poor graphics card. When I do this on my wife's computer, which is a fancy i7 with a high-end NVIDIA graphics card, it rotates things. It's almost like you look like it's spinning like a top. So unfortunately, mine's spinning very slowly. But I hope most of you can see the three-dimensionality of methane there. So that's very powerful. I'm going to stop the auto rotate now. To stop it, you just click it the second time. Okay. Now, if you want to just move it by hand, you can just do this 3D rotate and you can rotate around. And again, because my computer really sucks. I'm sorry, that's very bad language. My computer is very poor. I can't rotate mine very well. I can do it kind of slowly. Yours, I can guarantee you got a better computer than I do. And you're going to be able to do some nice stuff here. All right, so there's methane. I'm going to go ahead and close this out. I don't really want to save this, so I'm just going to close that out. And so we're going to get back here. So the screen share is stopped. Okay. That was a very brief introduction to ChemSketch. ChemDraw works identical, by the way. ChemDraw is very, very similar. So you Mac people who have the you actually even have more tools than that freebie program, although that's very powerful. But that kind of gives you just a very brief introduction. So if you would, get in this weekend, play with it, put in all kinds of stuff. Again, you cannot hurt anything. So I hope you have fun with it. And we're going to do a whole lot more with this on Tuesday. we're going to do a lot of hydrocarbons. Okay. So that is it for our discussion today. I'm going to open it up to the floor for anybody that wants to ask me any questions. We've got about 5-10 minutes left. So please feel free if you got something you need to ask.
Hi, Dr. Brown.
Yes.
So I have a question about like Tuesday's class. Will that be in person or will we still?
You know, I'm going to
online?
let everybody know this weekend. I'll let you know. I'll let you know on Saturday. I was hoping, to be honest with you, I was hoping this COVID was coming down, but the university contacted me this morning. It's actually still, we're hopeful it's going to crest. It's coming soon. I'm not a medical doctor. I'm not an epidemiologist. I can't tell you this for a fact, but the university has a physician on hand, and I've been talking to her several times, and she's optimistic that we are going to crest, but not until next week. So we're still going up, unfortunately. This is really tiresome, but you know, we got to do what we can do. So if we're still cresting, you know, we may have to go Tuesday online again and just kind of take it day by day. I'm hopeful Tuesday we can gather in person, but you know, I'm going to talk to the physician. I'm going to talk to Dr. Hentz later this weekend and get her opinion and see what she says. And then I'll let everybody know probably Sunday or Monday, whether we'll either be a Zoom again, or we're going to go just everybody gather in Dabney 222.
Okay, thank you so much.
I had a question about the homework.
Sure.
So I guess in terms of like the homework structure and whatnot,
Right.
is it going to be like just like one attempt per homework, or are we going to be able to work towards a better grade in regards to like multiple attempts on the homework?
It'll basically be 3 attempts, and I choose the best one, and
Okay.
it's all done through Moodle, by the way. It's not WebAssign. Hopefully most of you have had a Moodle quiz or a Moodle homework before. Some have, some have not. Don't worry about it. It's very straightforward. You know, it'll be, once you get on, you know, we'll work through like a dummy homework to start with. I'll give you one assignment that's just not worth anything. I'll ask you your favorite color. I'll ask you the name of your pet if you got one, you know, just to get you used to the homework tool that's on the Moodle quiz. But that's basically it. And, you know, you shouldn't really stress too much about the format. It's pretty straightforward.
Okay. Thank you.
You're welcome. Everybody else okay? Yeah, I know you have to get off to other classes now.
I
Yeah,
actually
yeah.
have a quick question.
Yeah,
So
please.
I have my boyfriend took your Chem 221 class, and he gave me like the plastic like chemistry modeling kit that he used a couple years
Right.
back. Would that still be a useful tool for this class?
I love hard models. You know, I know that program I just showed you. You know, it's basically a computer version of that model kit you just had. But I've been doing chemistry for 45 years, more than that, close to 50 years. And there's nothing like holding the molecule in your hand and rotating it around. So models are not required, but if you want to go ahead and just build methane and hold it in your hand, I tell you, there's something visceral about that. It's like my mother used to play violin, and she always said there was something that she loved about the violin because she felt the music. It through her hands, through her chin, through her shoulder. The music was more than just through her ears. And that's what models can do for you. Rather than just looking at with your eyes, to hold a 3-dimensional structure in your hands is something quite powerful. And I think it gives sort of insight that a model can't give you.
All right, that's great to know. Thank you.
You're welcome. There he is.
Professor, I was wondering what we should do like homework and reading wise, just to practice the stuff we did on Tuesday and
So-
today.
So you know the in the schedule
Yeah.
here. Let me. Here, I'll pull this up. Let me share my screen. Can everybody see this? No.
Yes.
Yes, you can. Okay. Do you see this column over here?
Mm-hmm.
So GOB 1 through 4, and then V1.17. Let me show you what that is. So if you go to those books, this is General Organic and Biological. So this is that book. I have to stop the share and come back again. Sorry. I have to kind of bounce back and forth, unfortunately. So I'll share the screen again. And now I'm going to bring up the Moodle page. Do you see this thing that says GOB? General
Yes.
Organic and
Yep,
Biological?
I looked at that. Mm-hmm.
You did? Okay, good. So there's a lot of great information here. Depending upon, has it been a while since you've had Gen Chem? Or have you had it recently?
No, it's been a while. I still remember
So, like-
parts of it, but I need like the more specific review.
Yeah, yeah. So if you get in here, that's where you'll see it. So you'll see things about acid-base chemistry. You'll see things about electronegativity. You'll see information about bond length, bond strength. We didn't really talk about that. We will talk about that maybe next class, or at least maybe in a few classes, where we'll talk about the length of the bond and the strength of the bond, because that's another important concept. So this is GOB. Now, in that chart, it also had V 1.7. So you see this V here? So go to volume 1, chapter 7, and you'll get all those readings related to that stuff that we had talked about. And there's great problems in there too. Now, I'm not going to assign any to you because there's so many people with varying backgrounds of general chemistry. Some of you just came right out of general chemistry. You just had it last semester. And if that's the case, wow, you have a leg up on everybody else because everything is fresh in your mind. But for those of us who's been in a little while, I would go to V1, that's V1, volume 1, chapter 7. Go to here, 1 through 4 chapters. Now that's a lot of stuff right there. But the 1 through 4 chapters is all that general chemistry stuff that you probably, I think once you kind of browse through it, things will come back to you a lot quicker. Like maybe you didn't understand the concept of electronegativity much when you first took Gen Chem. But, I tell you, when you look at it a second time or a third time, now things get to be much clearer in your head and you'll be able to understand it in a much deeper way. Okay. So that's what I recommend you do. Go to those textbooks and do problems if you want. I'd do a few, just to kind of prove to yourself that you understand what a Bronsted acid is and a Bronsted base, and what a Lewis acid is and a Lewis base. That whole concept of atomic structure, the electronic nature of an atom, 1s2, 2s2, 2p6, 3s2, 3p6. I know that's boring to you, but it does at least help us to understand where a lot of this chemistry is coming from. Everything comes from the atoms. Okay.
Got it. And where do we download ChemSketch?
ChemSketch. Okay, so let me show you that. I have to stop my share, sorry. Share screen. Let me get to the syllabus. See the syllabus? See this link right here?
Yeah.
ChemSketch. Just do this. Just copy and paste it into your browser, and it'll come up. Now, be careful here. There's 2 versions of ChemSketch. This is a very powerful program, by the way. Industries pay thousands of dollars a year for this site license. But this company, because they are very academically inclined, they give it to academic people for free. So do not choose the commercial version, because then it's going to ask you for a credit card. And if you put in a credit card, you're going to be $1,500 down on that credit card, and you're going to get letters from your parents. Choose the freeware version. They're the same. And now the commercial does have a few extra modules. I shouldn't say they're exactly the same, but everything we need is in this ChemSketch program. Okay. Now, if you're a Mac user, again, go to, or if you're a PC user, if you want to try the Mac program that I sent out everybody, you could try ChemDraw. That's the university gives us for free. So just go to OIT, NCSU, the OIT, and go to software, and you'll see all kinds of stuff. So you'll see, Adobe is there. A lot of the MATLAB programs are there. You'll see Windows programs. You'll see SAS programs, but you'll also see ChemDraw, and that's a great program too for either Mac users or PC users. They all work the same. Okay, there you go.
Thank you. That was really helpful.
No problem. Everybody else okay? All right, sounds great. Well, everybody have a great day, a fine weekend. Stay safe, stay healthy, and be prepared for a email from me this weekend about what COVID has for us in the near future. I'm as tired as you are, believe me. Okay, bye everybody. Have a nice weekend.
Thanks. Have a good weekend.